Hello, my name is Nady Carmona Aguilar, and in the following video, I will be talking about my work entitled DFT Simulation and Experimental Analysis of the Absorption Spectra of 2C and 2A. First, I would like to thank the audience for their interest and attention in this poster presentation. The topics we will cover in the presentation are, first, the main objective, followed by a brief introduction. We will also discuss the steps necessary to perform the simulations, continue with the results obtained, and finally mention the conclusions. The main objective of this work is to validate the simulations of the UV-Vis absorption spectra of the organic molecules 2C and 2A, which were carried out using the free software ORCA. This was done by comparing the results obtained by ORCA and analyzing the absorption spectrum obtained experimentally. Organic molecules have become significant in modern technology, playing a crucial role in various applications such as electronic devices, renewable energy, and pharmacology. The efficiency of these systems relies heavily on their electronic properties, including molecular orbitals, energy gaps, and density of states. Experimental characterization of these properties is often expensive and complex, leading to the emergence of density functional theory, DFT, as a powerful computational tool. DFT can predict electronic properties accurately and affordably by focusing on electron density. This computational approach addresses the many-body problem in quantum mechanics and is based on the principles outlined in the Hohenberg and Kohn theorems of 1964 and equations of Kohn-Sham. ORCA, which is a software that uses DFT to study molecular systems, allows us to solve these equations using different approximate functionals by means of an iterative, self-consistent field procedure. ORCA has several tools, but as far as this work is concerned, we will focus on taking advantage of the fact that this software simulates UV-Vis spectra using TD-DFT, time-dependent density functional theory, calculations, which facilitates the interpretation of the experimental spectra. The steps required to perform the simulations using the ORCA software are divided into three main sections. 1. Optimize the geometry. 2. Obtain the UV-Vis spectrum. 3. Plot the spectrum. However, before optimizing the geometry of the molecules, it is necessary to draw them using a graphical interface, such as Avogadro or ChemSketch software. In addition, the type of input files accepted by ORCA are INP files that can be generated by a graphical interface such as Avogadro. Once the .inp file has been obtained, the functional and the basis set must be specified in the input file, which in this case was the B3LYP functional and the DEF2 TZVP basis set. In image 1, we can see the optimized geometry for molecules 2A and 2C. Next, we generate the table needed to plot the UV-Vis spectrum. This is done by adding the command CM before the basis set and functional in the INP file containing the coordinates of the molecules with the optimized geometry. Immediately after the functional and the base, we specify in the file that the molecules are dissolved in dimethyl sulfoxide, DMSO, solution with the CpCm, DMSO, command, as shown in the image. Note that now the corresponding calculations will be carried out by the time-dependent density functional theory, or TD-DFT. Finally, we take the intensity and wavelength data from the table generated with ORCA and plot them using the UV-Vis PY program. It should be noted that the numerical calculation results obtained with ORCA only symbolize the transition probabilities between states, but do not directly represent the experimental UV-Vis spectrum. That is why, in order to compare the experimental and simulated results, a Python program is used, whose job is to apply convolution to the raw data from ORCA. The experimental absorption spectra of compounds 2A and 2C were obtained in the range from 200 to 1100 nanometers. An absorption onset was observed around 350 nanometers for compound 2C, corresponding to a forbidden band energy of approximately 3.54 electron volts. This value indicates the presence of a direct band, as evidenced by the linearity observed in the top plot for n equals 1/2. In the case of compound 2A, the onset of absorption was detected around 400 nanometers, indicating a forbidden band of 3.10 electron volts, also of a direct nature. Next, the experimental spectra were compared with theoretical simulations obtained using density functional theory, DFT, with ORCA software version 5.0.4. The simulations of compound 2C showed prominent peaks at 215 nanometers, 260 nanometers, and 334 nanometers, while compound 2A showed significant peaks at 216 nanometers, 276 nanometers, and 330 nanometers. Based on the results obtained, we can conclude the following. 1. Compounds 2A and 2C exhibit direct bandgap semiconductor behavior, with values of 3.10 electron volts and 3.54 electron volts, respectively. 2. There is good agreement between the DFT simulated spectra and the experimental data, which validates the use of theoretical methods as a complementary tool for optical characterization. 3. The small differences observed between the simulated and experimental spectra may be due to exciton interaction effects or the solvent modeling used. 4. The compounds studied show potential for applications in optoelectronic devices thanks to their optical properties and direct band nature.